Hi everyone. In this tutorial, I want to discuss with you a new method that we added to Topology.Pi, which is called Topology.SubCombinations. And it is a way to generate a large number of combinatorial subcomponents from a topology. And I'll explain what that means. Basically, as I posted on LinkedIn, this is due to my discussions many years ago with George Siney, where he said that computers cannot really do shape grammars because the idea of a subshape within a shape is a visual and perceptual one rather than an algorithmic one. So what does he mean by that? Basically, if you have, let's say, a cell complex, a kind of a series of boxes that are connected to each other, it does not mean that the subshapes are only the boxes, but they can be combinations of the boxes, or it can be even combinations of the edges or the faces. And not even by the endpoints of these edges. It can be any subshape, which could be an infinite number. For computers and for algorithms, that means a combinatorial explosion, meaning that finding all the possible subshapes becomes an intractable problem. So how do we solve this, and how do people who do shape grammars solve this? Basically, they guide the user through what is a relevant subshape, and they make assumptions about that, and they create things that are hopefully useful in the design problem that they are addressing. And this is what we are doing here, of course, the same thing. So let's start. Let me show you this tutorial, and I think some of the issues will become clear. Now, what can you give to this method as an input? You have to give it what is called a connected topology. A connected topology means that it has more than one subtopology. Something like a vertex would not be a connected topology. In this case, we are also talking about edges not being useful, because an edge is really, in Topology.Pi, is made out of two vertices, and therefore the two vertices are not really going to help you much. You can just simply get them. So we're talking about more complex shapes that have many components that are connected to each other. And what are those? Those, as you can see here, highlighted in gray in the second line. They can be a graph, and I'll talk about that a bit later. A cell complex, so a cell complex can have sub-cell complexes in it, made out of a series of cells, or it can have shells, sub-shells in it, that are made of a series of faces. A cell can have multiple shells as part of it, so you can imagine out of a cube, you can take 2 or 3 faces and make a shell out of them, and you can do different combinations. Same thing applies to a shell. You can take multiple connected faces and make a subshell out of it. And for a wire, you can take a set of connected edges and make a subwire out of that. Now, if you choose to use a cluster, you have to specify what kind of subtopology you want. But we are recommended that you really avoid clusters if at all possible, and just stick to the other types of topologies. Now, for graphs, you can get subgraphs, and that's quite intuitive and quite easy. So when we do this method, we can specify the minimum size and the maximum size. And what is that? That is the number of elements or sub-elements in each combination. So you can say, I want combinations that have anywhere between 2 and 6 sub-elements, or 2 and 6 cells, or 2 and 6 faces. And it will generate a set for you that is balanced, meaning that it will have equal amounts of each type of subcomponent that you have asked for. You can also specify the maximum number of combinations in order to limit the time of creation. So you can specify that using a variable called max combinations. And of course, that number is not guaranteed to be reached. You can also set a time limit, because some of these can be quite time consuming. So you can set a time limit in seconds, and it will stop after that and give you back what it has found so far. All right, so let's get started. As usual, the first cell is only needed on my computer, this one here, to import sys, and therefore you can skip running that. This, by the way, this Jupyter notebook is available on GitHub. It's called Combinatorial Sub-Components, and you can find it under the Notebooks folder on my Topology.Pi GitHub. So I will run this one first. Then I will import all the required libraries. Okay, and then I will check the version. It's always good to do this. So as you can see here, I print helper.version, and it needs 0.35 or newer. So helper.version doesn't just print the version, it actually goes out and checks on the web what pipe has, where you download the topologic pipe from, and it will tell you whether it's the latest one, whether you're behind, or whether it's even newer than what you have there. So 0.8.35 is the latest version as of this video. Okay, so now let's generate subcombinations of a cell complex. And since we are not going to specify the type of subtopology, it will automatically default to cells. But you can change that later on, and I'll show you how to do that. So first things first, let's create a prism, a simple cell complex prism, which is 3 by 3 by 3, and let's display it. Here we go. So this is our initial shape. So now we are going to create a list of combinations, and it will be a list of cell complexes that are subtopologies of the above cell complex. Okay. Now, here is something to note. The time limit that you see here, 10 seconds, only applies to generating the numeric combinations, not the actual cell complexes, because these will take much longer to create. Okay. So this is just simply giving the algorithm a time limit to generate the possible combinations and grow them and do a breadth first search in order to get you those combinations. Now, the time that is needed to actually convert those numeric lists to a cell complex by picking the cells, let's say, from the original cell complex, will take longer. So it might run for longer than this time limit, or it might even run for shorter than this time limit if your number of combinations is small. So let's see what this one gives us. So we're giving it, basically, we say Topology.SubCombinations here. We're giving it CC, which is the cell complex that we generated, this one here. And then we're giving it a minimum size of 2, so minimum of 2 cells, and a maximum size of 6, maximum of 6 cells. And in total, we would like 10 combinations. So these 10 combinations will be distributed evenly between combinations that have 2 cells, combinations that have 3 cells, 4 cells, 5 cells, and 6 cells. Okay, it will divide 10 by those, and it will try to give you a balanced list. And we're setting the time limit to be 10 seconds. So let's go ahead and run this for 10 seconds. And you can see here it's starting to take longer. This is now the phase of creating the cell complexes. So it took another 4 seconds to create the actual cell complexes. And it says it generated 10 cell complex combinations. So we are successful. We got the exact number that we asked for. And this is now saved in a variable called CC combinations, cell complex combinations. So let's go ahead and display those combinations one by one. So if you are running this on your laptop, if you downloaded this Jupyter notebook, you can change what n is here. So from 0 to 9, because that's the index here for 10 cell complexes. So let's go ahead and run the first one. And so that you know, it is also ordered from the smallest number of components to the largest number of components. So N0 should have only 2 components. Let's go ahead and check that. That's indeed what is going on here. So this is a cell complex, this beige one here. So let's go ahead and draw the last one, which is index 9. And as you can see, this is a larger one. It has 1, 2, 3, 4, 5 subcomponents. So it did not manage with the time limit, it seems, to find 6 components. So 1, 2, 3, 4, 5. No, this is 6, excuse me. This is 6. Yeah, 3 and 3. Yeah, so it did. So that's good. It has a good thing here. And let's go ahead and do something in the middle. Let's say 3 or 4 maybe, or 5. Let's do 4. And let's see what it gives us. Yeah. So this one has 4 subcomponents. Okay. So that's what it is. You can get them all. You can draw them. You can operate on them. Now it's a list of cell complexes. Now, what about if we want to find shells? We want to base it on finding different surfaces rather than volumetric cells. you can do the same thing. So let's go ahead and do that. So we're going to call that shell combinations. We use the same call, Topology.SubCombinations, but we give it a subtopology type of face. And it will figure it out for you. So it will look at what CC is, says, oh, okay, it's a cell complex, and this is a face, therefore I need to give him or her shells. So we'll do that. Again, same thing, from 2 faces to 6 faces in the shell, and a maximum number of combinations of 10. And as I said before, these combinations are always connected. You cannot get disjointed faces. It will always be a shell in this case, or it will always be a cell complex in the previous case. So let's go ahead and run this for, this time we're giving it 30 seconds. And it generated very quickly 10 shell combinations. So you can only ask for 10 combinations, so it found them in 1.4 seconds. So let's go ahead and display them. And here is one shell. As you can see, it's open. I mean, even if you find something that is closed, that looks like a cube, like a cell, it's actually a shell. It's just happened that these faces are closed up. So let's go ahead and do number 9, index 9. And here's another one. And let's do one more. Let's say the first one, it should have only 2 faces. And there it is, only 2 faces. That's a shell of 2 faces. All right, good. So now let's do the same, but for a graph. So first thing first, we're going to create a graph from the cell complex, a dual graph. And we're asking it to also include a vertex for every external topology, like all the exterior faces will get also a vertex and get connected. So let's go ahead and draw that. All right, so this is the graph, as you can see here. These ones here, 1, 2, 3, are the cells, and these peripheral ones are the faces. So that is a connected graph. So let's go ahead and create subgraphs out of it. We can say, again, same thing, Topology.SubCombinations. We're giving it the graph as the input topology. Minimum size 2 vertices. So when we're talking about graph, and we are, I think it's only defaults to vertices. I don't think I can do edges at this point. So it's from 2 vertices to 8 vertices. What you should also note here is that when you ask for, let's say, 2 vertices, you might actually get 4 vertices, simply because it's going to also include all the edges connected to those 2 vertices that it found, and that will give it more vertices at the other end of that edge. So just be aware of that, that it's not going to actually have just 2 vertices. So let's go ahead and run this. We're asking for 50 combinations and we're giving it 60 seconds, but actually graphs run really, really fast. So you'll find that it will get done in a couple of seconds. So 0.2 seconds even, so really fast for this one. And it generated 49 subgraph combinations. All right, so let's go ahead and show this. So here is the 48th one or 49th one, as you can see here. So let's do one early on, let's say in the index 10. Index 10s are smaller. Another one, let's say index 30. And here is another one. And as you can imagine, they are always fully connected. And that's it. If you have any questions, as always, please reach out either on LinkedIn or by email, and I'm happy to answer your questions. Thank you for watching.